In this video, we're going to be examining the effect of gas pressure changes on equilibrium systems that only contain gases. Pressure is important to consider because of the relationship that pressure has with the volume of gases, which we can see in the universal gas equation, PV is equal to nRT. We know that pressure and volume have an inverse relationship in order for this equation to be true, meaning that if we increase the amount of pressure that gases are subjected to, that means that we're going to push gas molecules closer together such that they occupy less space, and therefore the volume of that gas is going to decrease as a consequence of this pressure increase. Now, since the formula for concentration is moles of gas divided by the volume that they occupy, if we decrease the gas volume, the concentration of that gas must increase as a consequence of this, just based on the formula. So we can see that gas pressure changes actually result in a concentration change. The problem is in gas reactions or gas equilibrium systems, we have gases on both sides, which means that we're not just increasing the concentration of one gas, we're actually increasing the concentration of all of them. Now, to analyze these more effectively, we need to refer to pressure, and the first thing that we need to figure out is whether the products or the reactants are what we call the high pressure side or the low pressure side. And we can determine this simply by counting the number of gas particles that exist in the reactants and the products. For example, in our reactants, we have 2 molecules of nitrogen monoxide and 1 molecule of chlorine for a total of 3 gas particles in the reactants, whereas we only have 2 gas particles in the products. So because the reactants have a greater number of gas molecules, those gas molecules can exert more force than 2 molecules, and therefore the reactants are what we consider the high pressure side, because the more gas we have, the more pressure it is able to exert. Conversely, because the products have fewer gas particles than the reactants do, this is what we consider to be the low pressure side. Now, determining the high and low pressure sides of a chemical reaction is very useful in helping us to make an equilibrium shift prediction based on the maxim, whatever we do, the equilibrium will try to reverse. So if we were to increase gas pressure, that would mean that the equilibrium would want to take the pressure that we have increased and decrease it in order to reverse the change that we made. And we can do that by pushing the equilibrium away from the high pressure side to the low pressure side, such that we decrease the amount of gas that we actually have in the reaction and cause the pressure to decrease. So the equilibrium shift we would expect to see in this case, we would expect a pressure increase to shift the equilibrium to the side with a lower gas pressure, meaning to the side with fewer gases. Now, how do we justify this based on looking at the rates? Well, the answer is based on that relationship between pressure, volume, and concentration. So as discussed, pressure increases cause gas volumes to decrease because an increase in pressure pushes the gas particles closer together, meaning that the gas particles are now in a smaller volume, which means that they can now have more collisions more easily with each other, and this implies that gas concentration is going to increase. Now, because the reactant particles have more gas particles than the product side, that means that the concentration increase in the reactants is going to have a bigger effect, because if there are more gas particles in the reactants than the products, it's more likely that the reactants will have more successful collisions than the product side is going to. And therefore, even though we expect both rates to change, both rates to increase because of this concentration increase, we would expect the forward rate to increase faster than the reverse rate because, again, there are more gas particles in the reactants, which means a decrease in volume will result in even more collisions in the reactants than in the products, and therefore we have an imbalance. We have a forward rate that is faster than the reverse rate, which means that our equilibrium is shifting to the product side. So because of this, the concentration of reactants is going to decrease as a consequence of the equilibrium shifting toward the products, and the concentration of products is going to increase, meaning that if we have less gas than before because we're shifting the equilibrium to the side with fewer gas particles, the overall system pressure is going to decrease as a consequence, which is exactly what we predicted. It's because the equilibrium is shifting in this case to the products, which is the side that has fewer gas particles and therefore the low pressure side. Now that must mean that the opposite must be true in terms of pressure decreases. So if we go by the maxim, whatever we do, the equilibrium will try to reverse. If we decrease the pressure, the equilibrium will naturally want to compensate by causing an increase in pressure, and we can do this instead of shifting to the low pressure side. The equilibrium can shift to the side with a higher gas pressure, which is, in this case, the reactant side. But how do we justify this based on rates? Well, as we know, pressure decreases have the opposite effect on concentration, because if we decrease the pressure that gas molecules are subjected to, we remove force that keeps the gas particles together, which means they have more space to move around, so the gas volume increases, meaning that there are going to be fewer collisions between them because the gas concentration is now lower. Now, because, again, the reactants have a greater number of gas particles than the products do, in the same way that concentration increases have a bigger effect on the reactants because they have more gas particles, that means that the same effect is going to happen because of concentration decreases as well. And again, when we have a concentration decrease, we expect that both the forward and reverse rate are going to slow down, but because of the number of particles, they're not going to slow down at the same proportion. So because the reactants have a greater number of particles here, we would expect that a concentration decrease would have a bigger effect on this side than on the product side, and therefore we would expect that the forward rate is going to decrease faster than the reverse rate, and therefore we have a situation where our reverse rate is greater than the forward rate, causing our equilibrium to shift back to the reactants. Now, as our concentration of reactants increases because the forward rate is now greater, that means our concentration of products is going to decrease, and because we're pushing the equilibrium toward the side with a higher pressure, we're making more gas particles from a side that has less, and the more gas particles we have, the higher the pressure is going to be, which is why this results in a pressure increase. In the next video, we're going to look at the effect of catalysts, both inorganic and biological catalysts, on dynamic equilibrium systems.